In this video, we'll explore random variables in general and discrete random variables in particular. Consider an example. Suppose we roll 3 fair 6-sided dice. Then there are 6 cubed, or 216 possible outcomes. Up until this point, we've focused on possible events associated with such an experiment. For example, we might be interested in the event A that we roll all 6s, or event B that we don't roll any 6s. And we can express the uncertainty in these events by calculating their probabilities. In this case, there's a small chance that we roll all 3 6s. The probability is 1 6 cubed, or roughly 0.005. It's much more likely that we don't roll any 6s, with a probability of 5 6 cubed, or roughly 0.579. Consider another point of interest about the experiment. Let x be the number of 6s that we observe in 3 rolls. Since there are 3 rolls, we might observe 0 6s, 1 6, 2 6s, or 3 6s. That is, x can be 0, 1, 2, or 3. Notice then that unlike our events A and B that either happen or don't happen, x is a numerical outcome of the experiment. In fact, x is what we call a random variable. The basic idea is that the value of x can vary from experiment to experiment according to random chance, hence the name random variable. More technically, random variable x is a function from sample space S to the real line R. For example, when applied to the possible outcome in which we roll 2 1s and then a 6, the function x equals 1. There's 1 6 in this sequence. When applied to the possible outcome in which we roll 2 1s and then a 5, the function x equals 0. There are no 6s in this sequence. In general, there are 2 types of random variables. First, a random variable x is discrete if its possible outcomes are listable, that is, if they are finite or countably infinite. Let's consider some scenarios. As in our example, if x is the number of heads in 3 coin flips or the number of 6s in 3 dice rolls, then x is discrete. It has a finite number of possible outcomes, 0, 1, 2, or 3. Or let x be the number of goals that are scored in a soccer or football game. In this case, we can also start listing out the possible outcomes of x, thus x is discrete. There might be 0 goals, 1 goal, 2 goals, and so on. Technically, notice that there's no upper limit to how many goals there might be in a game. Thus, the set of possible outcomes is infinite. But since we can start listing or counting the possibilities, the set is countably infinite. But not everything is discrete. A random variable x is continuous if its possible outcomes are uncountably infinite. Think intervals here. For example, let x be the diameter of a tree in inches. Then x might be 50.5 inches. But a tree is never exactly 50.5 inches in diameter. If we measure more precisely, x might be 50.538 inches, or 50.538002 inches, and so on. Mainly, we can't start listing out all of the possibilities. Rather, x can technically fall anywhere above 0 inches. Or x is in the interval from 0 to infinity. Similarly, suppose that x is the difference between a bus's scheduled arrival time and its actual arrival time. Since time can be measured on a continuum of precision, x is continuous. It can technically be anywhere on the real line, between negative infinity and infinity. For example, if the bus arrives exactly when scheduled, x is 0. If the bus arrives late, then x is positive, and if the bus arrives early, then x is negative. And again, technically, there's no bounds on this interval. In this video, we'll focus on discrete random variables x. Remember that to capture the uncertainty of an event, we can calculate the probability of that event. To capture the uncertainty of a random variable, we can build a probability model. This model specifies 2 important pieces of information: what values x can take, and the relative plausibility of these values. In the discrete setting, the probability model for x is defined by a probability mass function, p sub x of x. A valid PMF satisfies the following two conditions. First, the PMF must take values between 0 and 1. Second, across all possible values of random variable x, the PMF must sum to 1. Further, in the discrete setting, we can interpret the PMF as a probability. Specifically, P of x, evaluated at little x, is the probability that our random variable equals little x. Though the notation I'm using here is very conventional, and will continue to use it, it can be confusing at first. Notice that the big X in our formula represents our random variable. So, the big X in the subscript here denotes that this model describes X. And the big X in the probability calculation reflects the fact that the outcome of this random variable is unknown. It varies from experiment to experiment. In contrast, the little x represents a possible outcome of the random variable. For example, if big X is the number of 6s in 3 dice rolls, a possible outcome or value that we might plug in for little x is 0. To demystify these technical definitions, let's reconsider the example where we roll 3 dice and are interested in x, the number of 6s in the sequence. The first step in building the probability mass function for x is to identify the possible outcomes of x. To this end, recall that we might observe 0, 1, 2, or 3 6s. The next step is to calculate the probability of each one of these outcomes. Let's begin by calculating the probability that x equals 0. This can only happen when we roll 3 non-6s in a row, with non-6s being represented by the white boxes here. For each individual roll, the probability of rolling a 6 is 1/6. Thus, the probability of not rolling a 6 is 5/6. Overall, then, the probability of rolling 3 non-6s in a row is 5/6 cubed. In our PMF notation, this means that P of x evaluated at 0, or the probability that x equals 0, is roughly 0.579. Next, let's calculate the probability of observing x equals 1/6 in 3 dice rolls. This can happen in 3 different scenarios. The first roll is a 6, represented by the black square, and the last 2 are not. Or only the second roll is a 6, or only the third roll is a 6. The probability of any one of these sequences is 1/6 times 5/6 squared. For example, there's a 1/6 probability that the first roll is a 6, a 5/6 probability that the second roll is not, and a 5/6 probability that the third roll is not. Overall, then, the total probability that x equals 1 combines these 3 scenarios. The PMF evaluated at 1 is 3 times 1/6 times 5/6 squared, or roughly 0.347. Similarly, there are 3 scenarios in which we might observe 2 6s. Only the first 2 rolls are 6s, or only the last 2, or only the first and last roll are 6s. The probability of any one of these sequences is 1/6 squared times 5/6. Overall, then, the total probability that x equals 2 combines these 3 scenarios. The PMF evaluated at 2 is 3 times 1/6 squared times 5/6, or roughly 0.069. Finally, there's only one way to observe 3 6s. And the probability that we get a 6 on all 3 rolls is 1/6 cubed, or roughly 0.005. And this defines the last piece of our PMF. Stepping back, we've defined the following probability mass function for x, the number of 6s in 3 dice rolls. This PMF defines the possible values that x can take, and the probabilities of these values. Moreover, this is a valid probability mass function. All of the probabilities are between 0 and 1, and they add up to 1. We can also graphically communicate this probability model. The x-axis here represents the possible outcomes of x, and the y-axis represents their probabilities, or the value of the PMF at these values. Notice that we're most likely to observe 0 or 1/6 in 3 rolls, and it's very unlikely that we'll observe 3 6s. This plot also illustrates why P of x is referred to as a probability mass function. We observe a point mass at each possible outcome of x. Now, tables and plots are great. However, imagine that x has lots of possible outcomes, perhaps infinitely many. Writing out the probabilities of these in a table or plotting them can be tedious or sometimes even impossible. Thus, it's also beneficial to express a PMF in the form of a formula. To build a formula for our dice experiment, let's revisit some patterns in our calculations. First, remember that we calculated the probability of getting 1/6 by noting that there are 3 ways to arrange 1/6 in 3 dice rolls, and that each of these arrangements that has 1/6 and 2 non-6s has a probability of 1/6 times 5/6 squares. Similarly, there are 3 ways to arrange 2 6s in 3 dice rolls, and each of these arrangements has a probability of 1/6 squared times 5/6. Next, we calculated the probability of getting 0 6s to be 5/6 cubed. Though this appears a bit different than our other 2 calculations here, we can rewrite it in the same pattern. Mainly, there's one way that we can arrange 0 6s in our 3 dice rolls, and the probability of this arrangement is 1/6 to the 0 for 0 6s and 5/6 cubed for our 3 non-6s. Similarly, there's one way to arrange 3 6s, and the probability of any arrangement of this type, or the single arrangement of this type, is 1/6 cubed for our 3 6s and 5/6 to the 0 for our 0 non-6s. Notice then that there's a bigger pattern. We can write the formula for the PMF at any x as 3 choose x times 1/6 to the x times 5/6 to the 3 minus x. First, 3 choose x calculates the number of ways to arrange x 6s among our 3 dice rolls. Next, 1/6 to the x times 5/6 to the 3 minus x is the probability of any set of rolls that has x 6s and 3 minus x non-6s. There are x 6s, which each occur with probability 1/6, and 3 minus x non-6s, which each occur with probability 5/6. In conclusion, we can represent the model of x, the number of 6s in 3 dice rolls, by the PMF here. A critical piece of this formula is what we call the support of the PMF. The support defines the values for which the PMF is defined. Here, we specify that we might observe 0, 1, 2, or 3 6s in 3 dice rolls. Without this clarification, our PMF wouldn't specify the possible outcomes of x, thus wouldn't specify the probability model of interest. The same PMF, or this part of the PMF, might be valid for infinitely many different sets of x. It's this particular set here that can occur. Finally, it's important to keep in mind that probability models are just that, models. They're theoretical representations of reality. To consider what we might expect in practice, we can run some simulations. For example, I ran the 3 dice roll experiment 5 times. In 40% of these experiments, I rolled 0 6s, In another 40%, I rolled 1 6, and in another 20%, I rolled 2 6s. This means that in 5 runs of the experiment, I never observed a sequence of 3 6s in a row. It's not surprising that these observations don't perfectly match up with the probability model. I only ran 5 experiments. After increasing this to 50 experiments, I did observe each possible sequence, 0, 1, 2, or 3 6s, at least one time each. But proportionally, these don't quite match the probability model. Finally, after running 1,000 outcomes, my results are more and more reflective of the theory. Roughly 57.9% of the outcomes are 0, 34.7% are 1s, 6.9% are 2s, and 0.5% are 3s.